So before starting the general properties, let me write here all the elements for 21, 22 atomic number, 23, 24, 25, 26, 27, 28, 29, and 30. So the element with atomic number 21 is scandium. For 22, it is titanium. 23 is vanadium, and 24 it is chromium. 25 is excuse me, it is manganese. For 26 we are having iron, 27 cobalt, 28 is nickel, and 29 we are having copper, and 30 is zinc. All right, if we write the configuration for them, it will be argon 18 with yes 4s2 and 3d1. All right, and this will be 4s2 3d2. Okay, this will be 4s2 3d3. Now if we have to calculate the unpaired electrons, okay, now if you see here, we are having one electron in d orbital. That means scandium, it is having one unpaired electron, right? For titanium, you can say two electrons. How they are unpaired? This is how we draw d block, right? And these two, they are unpaired electrons, right? Right. For 3d3, that is vanadium, we are having how many unpaired electrons? 3. For chromium, the configuration is argon 18, right? And 4s2 3d4. We have already discussed that this is an exception case. All right, that for this I can write for chromium that argon 18, okay, 4s1 and 3d5, okay, to make it a transition element with half filled d subshell, right? So if we use this configuration for this chromium, then how many electrons we will be having? How many unpaired electrons we will be having? Yes, 4s1 and 3d5. How many unpaired electrons you see here? 5 in d orbital and 1 in s orbital, right? 6. All right. Now, for manganese, we are having configuration 18 for argon, 4s2 and 3d6. How many unpaired electrons we are having in d orbitals? Try to use d orbital like this and fill the electrons 1 2 3 4 5, and this is 6. These fours, they are having unpaired electrons. That means 4. Now you see, if you see here from 24th of the chromium, starting from this cadmium, the number of unpaired electron, it is increasing till chromium, right? But after the chromium, it started decreasing like 6 to 4, right? If we write the configuration for iron, what would that be? Argon 4s2 and 3d, uh, iron 4s2 and 3d6, right? This will be 3d5. All right, and the number of electron, it would be 5. Okay, this is having 4 unpaired electrons. Same in this case, 3d7. How many unpaired electrons in d orbital? 3. In nickel, how many electrons unpaired? 3d8, having 2 unpaired electrons, and again there is one exceptional case. All right, copper, it will be having argon 8 4s1 and 3d10. All right, we are removing one electron from outermost shell and putting it in d orbital to make it stable configuration. So how many unpaired electron for copper? We are having one unpaired electron in s orbital, right? For zinc, as the configuration is stable, so we are not having any unpaired electron in d orbital for zinc. All right. Now let me tell you how we calculate using these unpaired electron, how we calculate the magnetic momentum or magnetic moment, or say magnetic behavior of these elements or transition element. For magnetic moment, we use this formula mu is equals to n into n plus 2. Remember this. Okay. These unpaired electron, they can be represented as n. All right. Now, if I say to calculate the magnetic moment of scandium, what would that be? How many number of unpaired electron does scandium have? One, right? So by substituting in this formula, we can get that 103, right? Bohr magneton, that scandium is having this number of unpaired electrons. All right. Now, the transition element, they show paramagnetic behavior. All right. There are two types of magnetic behavior, paramagnetic and diamagnetic. Okay. How we can say that and this element is showing diamagnetic behavior? For the element having unpaired electrons, all right, it will be showing paramagnetic behavior. Now, if you can see here in this first series of transition element with 3D configuration, right? You can see which element is showing diamagnetic behavior, that is zinc. Okay, how it is showing diamagnetic behavior? Because it is not having any unpaired electron, right? So zinc in transition element of first series, it is showing diamagnetic behavior, right? So I hope you can calculate now the, if I ask you to calculate magnetic moment for cobalt. Can you do this? How you're going to do this? First, you're going to write the configuration for cobalt. You're going to write the configuration. What is the configuration of cobalt? It is 27. That is argon 18, 4s2, and 3d what? 7. Right? This makes 20 and 3d7, 27. All right. How many unpaired electrons are there? Yes. How many number of unpaired electrons? For cobalt, number of unpaired electrons is 3. How? As you can see here in d orbital, if we fill electrons here like this, now these three, they are having unpaired electrons. These two, they are having paired electrons, right? So this is how we can calculate number of unpaired electrons, and by using the formula for magnetic moment, that is mu is equal to under root n plus n2, we can easily find the magnetic moment. Okay, for 3, this will be 3 into 5, that is 15 bm. Bm is what? Unit for calculating magnetic moment, and it is termed as Bohr magneton. Magneton. Understood? Now, if I ask you which behavior, which kind of magnetic behavior does cobalt show? As you know that it is having 3 unpaired electrons, that means it is paramagnetic in nature. Understood the concept? I hope it is clear to you now. All right. Now let us read some other properties. Okay, starting from here. Right. You can also use the relation that paramagnetism to calculate the paramagnetic nature or say behavior of transition metal. We can say that it is having direct relation with N. What is N? that is number of unpaired electrons. Understood this concept, right? So for element having no unpaired electron, what we call them? We call them diamagnetic. Okay, they are termed as diamagnetic, right? So we have already discussed the example for cobalt also. Okay, I want you to try for nickel 2 positive, okay, and chromium 3 positive, okay, to calculate the uh, paramagnetic nature of these elements, okay, and to calculate their magnetic moment, okay, right. Can you do this, right? These are the oxidation state of nickel and the oxidation state of chromium, okay. Right. For this, let me write you here the configuration for chromium. It will become argon and 3d3. Okay. And for nickel, it will become nickel 2 positive. It will become argon. This 2 positive means loss of 2 electrons, right? So for this nickel, it will become argon 3d. All right. So I hope you can do now how we can calculate the what we call how we can calculate the magnetic behavior. Okay, now let us read here the other properties. Transition element, they displays general metallic properties. Why general metallic properties? Because they are mostly metals. Okay, so as you know, the properties of metal, they are generally, they show the property of ductility, malleability. They are hard. Okay, they are having high thermal and electrical conductivity. They are good conductors. Okay, they are having metallic luster and high tensile strength. Right. So similar to the properties of metals. Okay. So zinc, cadmium, mercury, and manganese, they are exception. Why? They are they exist in liquid form. Okay, so that is why they do not exhibit metallic properties. All right. So the greater the involvement of n-1d orbitals, okay, in addition to ns electrons, it makes the interatomic metallic bonding stronger and the melting point high. Now here we are reading its first general property, that transition metals, they are having high melting point. Okay, how they are having high melting point? Let's discuss this here. This first property we are discussing now, that transition metal, they are having high melting point. Okay, if I write it here, that transition metal, okay, for high melting point, for high melting point, why they are having high melting point? Because they are directly the melting point of this is directly proportional to the interatomic attractions. Okay, it is also written here that maximum that they are having interatomic attractions. What kind of interatomic reactions? Metallic attractions. Okay, because transition elements, they are mostly metals. Okay, so they show strong metal metal bond, metal to metal bond strength. All right, except these transition elements, except these transition metals. All right, right. So the transition element, melting point of transition element, they actually increases to its maximum till manganese, that is D5, okay, say 25th element with 25 atomic number, and then decreases regularly with increasing atomic number. Now why this happens? It is like, say, this we are having, this side we are having atomic numbers, okay, this side we are having temperature. It is like that transition for some atoms, it is increasing, okay, but for manganese it drops, or say it dips, and then it start decreasing. Okay, we observe greater dip in melting point of manganese, Okay, why this happens? Now there is a reason behind it, that manganese, okay, it has lowest, or say it shows dip in melting point, okay, than other transition elements. Why is it so? Okay, the reason for this is that melting point of manganese is very low is due to its uh, half filled configuration. What is the reason for manganese showing lowest melting point? Due to its half filled D subshell configuration. Okay, now how this impact? See, here I am writing configuration for d orbital for manganese. Okay, that is half filled, and here we are having 4s2 orbital, right? Now with manganese having this strong, or say stable, half filled d subshell configuration, so these elements they resist, okay, they resist and they do not take part in the chemical reaction. Okay, okay, as they are having strong metal metal bonding, these elements they resist and they do not participate, and only 4s electrons, okay, 4s electrons they participate and results in lowest melting point. Okay, so this question is very important, that why out of elements, that why the first series elements, okay, only the manganese it is showing the lowest, or say dip in melting point. Now if I write the graph here for melting point only for all these uh, transition elements, it will come like this. Say I'm drawing here the graph for transition series 1. Okay, and here we use some other color. Here again dip. Okay, now this is kind of curve, okay, with respect to the elements. Say this is scandium, titanium, okay, this side we are going till zinc. Okay, for first series, for second series, and for third series. Okay, so this is the graph of melting point, okay, for transition element series. All right, now how we define this? This is for third transition series. Okay, this is for second transition series. Okay, and this is for first transition series. All right, this is for first transition series. Right, now in first transition series, that is starting with scandium. Okay, in first transition series, that is starting from scandium. Here this dip we observe for manganese, and the reason I have already told you, that the d5 electrons in d orbital, okay, the 5 electrons present in d subshell in manganese configuration, they do not take part in the chemical reaction. Only 4s2 electrons they take part. That is why, due to their half filled, or say partially filled d subshell of manganese, they show dip in the melting point, or they show the manganese it is showing lowest melting point. Okay, same in the case of second transition series with this tc element, it is showing dip with the same reason. All right, as it is having 4d5 stable configuration, this manganese is having 3d5. But in case of fourth transition series, or say uh, third series, with 5D configuration, here we are having this tungsten W. Okay, this series it starts from HF, or say lanthanoid. Okay, And here W, that is tungsten, it shows highest melting point. Okay, why it shows highest melting point? Because the tungsten, it is having strong metallic bond. All right, first thing, that it is having strong metallic bond. Now as we are moving down, okay, in block D, what will happen? What is happening here? The atomic size of element, it is increasing, right? And which is why the ionization enthalpy of this element, it will be decreasing. Okay, so it is easy to remove the electrons due to the high atomic size, right? Which is why the tungsten element, it is showing high melting point. Have you understood the reason that why the element of third series, okay, this is first, second, third series, this is third, okay, with 5, which is also known as 5D series, the tungsten element, it is showing the highest melting point. Is it understood or no? Because as we are moving down the group, okay, the atomic size of element, it is increasing. With the increasing atomic size, the electron revolving around the nucleus, it will go far from the nucleus, right? So it will become easy to remove this electron, right? So the ionization energy will be low for such elements, right? So if the ionization energy is low, then although the metal bond will be strong due to its high size, the melting point will increase. All right. So the melting point of transition element, it increases to a maximum value if we talk about the first series. Okay, that is to D5 except for manganese and Tc. Okay. Otherwise, then after D5, it regularly start decreasing. Why it start decreasing? Because after D5 configuration, D6 to D10 configuration, there will be a pairing of electrons, right? Like this, right or wrong? For D6 to D10, the electrons, they will start pairing, right? Which is why the melting point, it will start decreasing. Understood? Right. So here one question I want to discuss with you, that we see that these elements, zinc, cadmium and mercury, they do not show metallic properties, and as and I have said that mercury, it exists in liquid form, right? Now number of times this question have been asked in the exam, like why mercury is liquid, okay, or why it exhibit liquid state, that why it is having liquid state. So the answer for that is because all the last members, okay, of D block series, all the last elements of, or say members of D block series, that is these zinc, cadmium, mercury and manganese, they have low, or say they have weak metallic bonds. All right, they are having weak metallic bonds, okay, and as they are having weak metallic bonds, they are soft metals. All right, they are having weak metallic bonds and they are soft metals, and they have low melting point, okay, which is why if we look at the configuration, that's why if we look at the electronic configuration of these elements, how are they? 3D then 4s2, right? For this, for cadmium, it will be 4d10, 5s2, right? So with this configuration, they do not take part in metallic bonding. Okay, they do not take part in metallic bonding. Okay, which is why they are termed as soft metals, and they are basically in the mercury, it is having liquid state. Understood? Now, the next property is the number of electrons. It is directly proportional to the resultant bonding that we have already discussed, right? That the paramagnetic character, it is also directly proportional to the number of electrons that are bonding, right? It is the number of electrons which represent the bonding. Okay, right. Now the enthalpies of atomization of the elements. Now, what do we understand from this enthalpy of atomization? The next property transition element shows is the enthalpy of atomization, which is also represented as delta HA. Now, what is this enthalpy of atomization? This enthalpy of atomization is the energy, okay, energy required to isolate an atom from the solid state. Okay, to isolate an atom in to isolate an atom from the solid state. Okay, what is the enthalpy of atomization? It is the energy required to an atom from the to isolate an atom from the solid state. All right. So the enthalpy of atomization of elements of second and third series, they are greater than the corresponding elements of first series. Now why this happens? If I draw here the enthalpies, their enthalpies for 3D elements, the enthalpy of atomization, it goes like this. Okay. This is for 4D and this is for 5D. For 4 and 5D, we observe a very less difference in their enthalpies. Why? Why we are facing less difference in the enthalpy of atomization of 4D and 5D? Because they are almost having same atomic sizes. Okay, but if we move down the group, if we see here, this is the 3D series and this is the 4D series. If we move down, the difference between the atomic sizes from 3D to 4D is quite large. Okay, that is why this these second series and these third series, it is having higher atomization energies, okay, than the first series of transition element, that is 3D. Understood? Also, we can understand this concept with this, that enthalpy of atomization, it is directly proportional to the metallic bonding. Okay. Also, it is directly proportional to the number of s electrons and number of electrons present in d orbital. Okay, and also it depends on the interatomic attractions, the enthalpy of atomization. Okay, so 3D, the order for enthalpy of atomization is this. This is having less, and 4D is having more greater, and 5D is having even greater enthalpy of atomization than 3D. All right, it depends on the size. As moving down the group, the size of atom increases, right? Moving down the group, if size is increasing, the ionization energy will be decreasing. If the ionization energy is decreasing, then it means that metal bonds, they are strong. Okay, so that means that moving down the group, the metal bonds, they are getting strong. The enthalpy, ionization enthalpy is decreasing, the size is increasing, which result in the higher uh, enthalpy of atomization. Understood? Right. So let us move to the next property of atomic radii of transition element. Okay, atomic radii. atomic radii, and ionic sizes of transition metals. Now, if we read the first point here, the isoelectronic species, iso means same, electronic means having same number of electrons or having same charge. Okay, so isoelectron species are what? The ions which are having same charge. Okay, so the isoelectronic species, they show gradual decrease in radius. Okay, with an increase in atomic number. You can see here the atomic number is increasing, but the atomic radii is decreasing. Why? Because the nuclear charge is increasing. Okay, if the nuclear charge is increasing, if we talk about from D1 to D5, okay, the nuclear charge of element is increasing. Okay, and why? Because there is electron repulsion. All right, for D1 to D5, all right, the nuclear charge on atoms, it is increasing. It increases. Why? Because there is electron repulsion. All right, where is electron repulsion? In D subshell. All right, but from D5 onwards, or say from D6 to D10, all right, the electron repulsion, it will start decreasing. Electron repulsion, it start decreasing. That means nuclear charge will also decrease. Okay, why? Because the electrons after D6, after D5, they will start pairing like this. Okay, now from D6 to D10, there will be crowding like this, overcrowding. The electron, they will start pairing. Okay, so the more electron being added to the 3D subshell, okay, so they will create almost similar transition elements for the particular species. All right, which is why we say that the atomic radii, it decreases after manganese. All right, so as I have discussed, the nuclear charge, it will increase in d electrons, but due to poor shielding in 4d in these d electrons, the electrostatic force between nuclear charge and the valence electron increases, and hence the atomic radius decreases. That means that d1 to d5, the nuclear charge will increase because electrons, they are not paired. Okay, but after d6, it will start pairing. Okay, pairing of electron will takes place, and there will be crowding of electrons in 3d orbital, which result in the decrease in atomic radius of elements in d or in transition elements. Okay, so if we read here the atomic sizes of series 3d, it will be greater than the 3d than the 4d series and 5d series. Okay, why it will be greater? Because moving down the group, atomic size will increase, ionization energy will decrease, and obviously there will be more electron pairing if we compare to 3d orbital in 4d and 5d. Understood? Now, if we talk about the filling of 4f orbital before the 5d orbital, it will also result in decrease in atomic radii. Okay, that is called lanthanide interaction. We will discuss in detail about the lanthanide contraction in next class. All right. So what we say here, that in 3d to 4D, okay, we are having large difference large difference in atomic radius. Okay, that atomic radius, it gradually decreases. Why it decreases? Because atomic size increases, right? If the atomic size increases, as we know that 4D and 5D, their atomic size are almost same. Okay, they are having same atomic sizes. Why they are having same atomic sizes? The reason is due to lanthanoid contraction. What is lanthanide contraction? We will study in detail in next class. Okay, so because of lanthanide contraction, their sizes of 4D and 5D transition elements, they does not have uh, much variety, or they does not have much difference. Okay, so if we talk about 4f, the nuclear charge is increasing because the size increases. All right. So there is one question that is commonly asked in exam based on this point of atomic radii, that why the zirconium ion and hafnium hafnium element, zirconium and hafnium element, they are same. Okay, they are having same atomic radius. Okay, or why they are having same size. Okay, why they have same size or same atomic number. So the reason for this question is lanthanoid contraction. Okay, if you can see here, zirconium, it is having atomic radius 160 picometer, and for hafnium we are having 159 picometer, of which is an element of third 3D series. Okay, they exhibit same physical and chemical properties due to lanthanoid contraction. All right. The shielding of 4f electron is less than that of d electrons. Why? Because it is having high nuclear charge and it is having larger atomic size. All right, let us move on to next property, that is ionization enthalpy. We have already discussed how the ionization enthalpy varies in uh, D block, right? So let us read here the ionization enthalpies. It increases from left to right. Okay, why it increases from left to right? Because the nuclear charge increases. Okay, but moving down the group, the ionization enthalpy decreases. Why? Because atomic size increases. Atomic size it increases, and the nuclear charge, okay, this nuclear charge will decrease. Okay, the nucleus, due to its higher atomic sizes, okay, it cannot shield the electron revolving around the orbital. So that is why the ionization, while moving down the group, it decreases, right? So ionization enthalpy, it exhibits fewer variation in transition elements compared to non-transition elements. Ionization enthalpy of successive elements, they show second and third in second and third series, they are much higher than the first ionization enthalpy. Obviously, by the ionization enthalpy, or say successive ionization enthalpy are what? They are high for second and third series. Why is it so? See, ionization enthalpy is what? It is the energy required to remove an electron from its outermost shell. Okay. So as we are moving, okay, as we are moving in series, okay, if we remove, if we are removing electrons, say from d6 orbital, okay. See, if I draw here d6 orbital, 1 second. If I draw here d6 orbital, 1, 2, 3, 4, 5, and 6 electron. Suppose I have provided or I have applied ionization enthalpy here, and I'm able to remove this one electron from this shell. Okay, that will be termed as ionization energy 1. Again, I'm applying, okay, some enthalpy or say some energy to remove and one more electron from its valence shell. Then it will require more energy, okay, than the first one to remove this electron from its outermost shell. Why? Because after removing this electron, if I remove this electron from here, see, this will attain the stable configuration, right? This will attain the partially filled or say half filled stable configuration, right? Now, if I apply one more time ionization enthalpy to remove this electron from its outermost shell, it will require more ionization enthalpy than the first one. So that is why the ionization enthalpy, okay, it will increase, right? Because after removing one electron in the transition element, the for second removal of electron, it will attain stable configuration, right? So ionization enthalpy for second and third series, they are high in transition elements, all right, and they are termed as successive ionization energies, right? The removal of electron changes the enthalpy of 4s and 3d orbital. This is clear, right? As we remove the electron, it will change the enthalpy of 4s and 3d orbitals, right? The nuclear charge uh, in d block, electrons are removed from ns, then the d orbital. This is clear. We have discussed in this electronic configuration that we have discussed the exception cases of chromium and copper, right? With this, when we are writing the configuration for chromium, we write it as argon and 4s1 and 3d5. The electrons, they are removed from the outermost shell of 4s first, okay? Why? Because to a table uh, to attain a stable configuration, right? We remove electron from this 4s orbital first, then the d orbital. Okay. The nuclear charge, it increases from scandium to zinc in 3d series. This is understood by moving left to right. Nuclear charge increases, and that is why the ionization enthalpy increases. Okay. How the nuclear charge increases? Because number of electrons, they are adding to the same shell, right? So thus the shielding of 4s electron, that is more effective than the outer electrons. Okay, so that we can say that the slight increase in ionization enthalpy, it will observe in 3d series while moving left to right. Okay, so if we consider the configuration without 4s electrons, suppose in d orbital we are not considering the configuration for 4s, then this dn orbital, or say d10 configuration, they will be highly charged ions. All right. Now, due to poor shielding of d orbitals, okay, the second ionization enthalpy increases, that we have already discussed. If we look at this table, the green color is for 3d transition elements, okay, that moving from left to right as a nuclear charge is increasing and due to poor shielding. Okay, for other series, the second ionization enthalpy, it is decreasing. Okay, see, for second element it decrease, then it increase, right? For manganese 2 positive and iron 3 positive, they exhibit exceptions in increasing ionization enthalpy. Okay, why? Due to half-filled stable D5 configuration. I hope this concept is clear to you now. Okay, how this electronic configuration, it varies different properties of transition element, whether it is ionization energy, okay, or whether it is um, the what we call this atomization enthalpy, right? Now, the factor responsible for ionization enthalpy, they are the attraction of electron. We know this ionization enthalpy depends on the nucleus and attraction towards the electron, right? So repulsion between the electrons, if there will be repulsion between the electrons, then there will be exchange of energy, and this exchange energy, it will increase with the increase in pair of parallel spin in degenerate orbitals. Okay. Now manganese, it has a configuration of this. Chromium plus, it has configuration of D5. All right, you can see D5 and D5. So the ionization enthalpy Mn plus, it is lower than the chromium. All right. For iron 2 positive, these are some cases, exception cases that we are discussing now based on ionization enthalpies. That iron 2 positive, it will show lower ionization enthalpy than manganese 2 positive because of D6 configuration, while Mn positive, it will show D5. Now, what if any question will ask in the exam based on the variety or based on the difference in the increasing and decreasing of ionization enthalpy. You can use the concept of electronic configuration to answer such type of questions. All right. Now let us move on to the important property of transition element, that is oxidation state. Now transition elements or say transition metals, they shows variety of oxidation state. All right. For example, for manganese, we observe the oxidation state, it varies from +2 to +7. Okay. Now why there is a variation in oxidation state? That is because of electronic configuration again. Okay, that is because of, if I write here the electronic configuration of d orbital, it is like this: n minus 1, d 1 to 10, and ns 1 to 2. If you see here, there is very low energy gap between d orbital and s orbital, which is why the transition elements, they exhibit variety of oxidation states. All right, so if I can write here that due to small energy gap, okay, due to small energy gap between s and d orbital, that is why they show variety of oxidation states. All right, what will be the other reason? That the s electron, they can easily lose, okay, they can be easily lost, and the d electron can also easily lost due to this small energy gap. All right. So hence, smaller energy gap between ns and d orbital, it will result in the variation of oxidation state in transition element. Okay, but it causes, why it causes electron from both the subshell to participate in bonding. Okay. It causes electron from both subshell to participate in bonding. What bonding? Metallic bonding. All right. Now, if we read the concept here, the elements with great oxidation energy, they occupy the center of series. Okay, while two extreme end, they are having few oxidation. If we talk about scandium and titanium, they are having low oxidation state. Why? Due to presence of few electrons. Okay, while copper and zinc, they also have low oxidation state because of presence of d orbitals. Okay, now copper and zinc, due to presence of d orbitals and s orbitals, they the same thing, that there is small energy gap between s and d orbitals. Alright. Now the stability of maximum oxidation state is due to sum of s and d orbital that we have already discussed. Okay. The difference by the unity of oxidation state of transition elements, okay, that is due to incompletely filled d orbitals, again the same, and the oxidation state of non-transition element, it is increased by 2 positive, or say 2. Okay, so basically when we talk about oxidation state, we talk about the reduction state, whether there will be a gaining of electrons or losing of electrons. Okay, so you know that oxidation is what? It is loss of electron. Reduction is what? It is gain of electrons. Okay, so why, how the transition element, they are showing variety in the oxidation state? First is due to the small energy gap, and second thing is that due to this, it causes the electrons from both the subshell, from s and p, s and d, to participate in metallic bonding. All right. Now, the lower oxidation state, it will they are not favored by the heavier metals. Okay, in d orbitals. Unlike p orbitals, there is inert pair effect. All right. So the low oxidation state, they are found by complex ligand compounds have the ability. Now here come one more property, that transition metal. Okay, they form ligands, or they are very helpful, or they form number of complex compound. how they form number of complex compound. Say, let me tell you here how they are forming number, how they do the formation of complex compound. See, to form a complex compound, okay, I'm writing here in short, we need uh, small size, we need small size of D block metals, okay, and we need high ionic charges to attract ligands. Okay, ligands are what? Which are attached to the central metal ion. Okay, and we need an availability of vacant d orbitals, vacant d orbitals. All right, to form a ligand with the lone pair. Okay, for lone pair donation. Okay, now how they form complexes? Let me show you here. See, as I have said that coordination compounds, okay, or say coordination complexes, they are found when the lone pair donors, okay, lone pair donors, they donate their lone pairs to a ligand, okay. For example, say NH3 or say NH2O. NH3 is having lone pair, H2O is also having lone pair. So they donate their lone pair to who? To the transition metals, okay, and that is how they form coordination compound, okay, that is how they form coordinated complex ligand, okay. So transition metals, they are famous to form complex or say coordinate complex because they are easy to adjust with, because they are having different oxidation states, so they easily adjust, they easily accept the lone pairs or say pi bond, okay, and they form these coordinate complexes. All right, so this is one property. Now let us discuss one more tricky property of uh, transition metal quickly. All right, so for transition metals, this standard electrode potential we discussed in the chapter 3, that is electrochemistry. I think yesterday we have discussed about the standard electrode potential, that it is represented by E naught, right? So transition metals, for all transition metals, the E values or say standard electrode potential values, they are negative. Okay, all the transition elements, they show negative standard electrode potential values, okay, but there is only one element is there that shows the positive E naught value, okay, and who is that? That is copper. Okay, how it is showing positive electrode potential value? Because copper, it shows what? It prefer reduction, okay, due to its positive value. This reaction we have done in electrochemistry already, okay. Here copper is being in liquid, in aqueous state, it will attain solid state or say neutral state after reduction, okay. So that is why it is showing positive value. Now why copper is showing positive value? Why only copper? Because it involves metal ion, as in, because here as you can see the metal ion of copper is in aqueous medium, okay, it represent enthalpy of hydration, because the copper metal ion, it is present in aqueous form, so that is why it represent enthalpy of hydration, okay. And also after ordered arrangement, it leads to strong lattice formation. Okay, after strong arrangement, it leads to strong lattice formation. Okay, now if there is a lattice formation, that means it has strong enthalpy of atomization, which is very important. So in short, if I say that enthalpy of atomization, okay, it is much larger than enthalpy of hydration. This is a short answer for the question that why copper shows positive electrode potential, because copper being in aqueous form, okay, showing reduction or having enthalpy of hydration, it will form strong lattice. That means that it is having enthalpy of atomization, okay, that is much larger than the enthalpy of hydration, which is why the copper, it shows higher electrode potential value. Understood? This is very important point. All right, so let us read here the transformation of solid metal atoms, okay, depends on the thermochemical parameters, that how they are transferring to solid. That is this the example we have discussed for copper, that it is forming strong lattice, right? So the positive value of copper, the positive value of electrode potential of copper, it is due to inefficiency of liberating H2 from acids, right? So only oxidizing acids, nitric acid and hot concentrated sulfuric acid, they are get reduced by copper. So that is why the addition of first and second ionization enthalpy, it exhibit less inert values across the series, exception or say except copper, right? Right, now here we have given the trends of standard electrode potential that we have already discussed. All right, that the low value of this electrode potential in scandium vanadium, why it is due to its stability. All right, and high value of electrode, these all values we are discussing, they are having negative values. All right, that why they are having such values, negative values. And okay, so we have discussed here for all the elements of first series that why they show, on what factor they show this negative value. Okay, for Zn, because it is having D10 configuration, for manganese and for iron as they are showing D5 configuration, okay, half filled configuration, they have high inert values, right? Right. Now, trends of stability of higher oxidation state. Now here we have already discussed that the transition elements, they exhibit variety of oxidation state. For some we have discussed here, like for tetrahalides, okay, for BF5 and CRF6, they are having high oxidation numbers. Simple halides, they do not exhibit +7, okay, only MnO3 F is known. Okay, fluorine, due to its higher lattice energy and high bond enthalpy, they form stable oxidation state. Copper 2 positive is more stable, right? So these are all the trends, okay, in high oxidation states in transition metals, right? Now the chemical reactivity, this we have already discussed, the chemical reactivity and the E naught values. All right, right. The magnetic properties we have already discussed, what kind of magnetic property they show, okay. The paramagnetic properties shown by unpaired electrons. If the electrons they are paired, for example in zinc, they will show diamagnetic properties. Now this is very important property of transition metal, that they form colored complexes. They form colored complexes due to DD transition. All right, how they form colored complexes? As you can see here, these are the example of complexes. Okay, this complex is formed by chromium, iron, cobalt, nickel. All right, so when an electron it absorbs light of definite frequency, All right, it moves from lower energy level, say ground state, to excited or say higher energy level. All right, when they absorb energy, see, we are having an electron here. When they absorb energy, they got excited from ground state to excited state. Okay, so as the frequency is increasing, it is moving from ground state to the visible region. Okay, so as they absorb light, they form it. As they're moving from lower region to higher region, or say moving from lower region to visible region, they exhibit color. Okay, the ligand and its nature determines its what type of ligand we are using. Okay, this determines the frequency of light it will absorb and the color it will um, show. All right. So how the complex formation, we have already discussed how the complex are formed when we need a lone pair donor to form complex, okay, with transition metal, right? These are the example given for complex compound where iron is forming complex with cyanides. Complex compounds are what? They are complex species, right? In which metal they, or say iron, it binds with anion or say neutral molecules. Okay. So due to its small ionic size, we are talking about iron here, and high ionic charging and the presence of d orbital, right? The condition I have already discussed with you. What are the conditions required for complex formation? Okay, lone pair, d empty d orbital, okay, and transition metal will accept these lone pair, all right, and it form a ligand, or say form bond with ligand, and they form complexes, right? Now catalytic properties. Catalytic properties are what? Let's take an example of hydrogen and iodide there. This example I think we have already discussed in electrochemistry also, where H2 and I2, they are combining and forming 2Hi, right? And while combining, they were forming an intermediate like this. Yes or no? Now what happened here is we add a catalyst here, okay, to increase the rate of reaction, right? Now what catalyst will do here? Catalyst will bind, okay, and decrease activation energy. This activation energy we have already discussed in chapter 3, okay, to form product. Okay, here we have given example of transition element, that is iron. That what is happening here, we are here iron, it is acting as a catalyst, okay, which is helping in forming product of the reaction. How it is helping? They will bond with the reactants, okay, and weaken the bond. Okay, that means it will decrease the activation energy and help the catalyst to bind with the reactant molecules to form a product. Understood? Right. Other property is that transition elements, they are homogeneous and they form alloys. Okay. Alloys of transition metals, they are hard and they have high melting point. For example, brass is an alloy of copper and zinc, and brass is an alloy of copper and tin, right? One more transition element property is that there is a formation of interstitial compound. See, this is a compound, it is having intersite. Intersite means the site, or say empty spaces, okay, present in between the compounds. Okay. Now what is happening here? The interstitial compounds are what? They are neither ionic or nor covalent. Okay. So with this, okay, they possess high melting point, okay, and high boiling point, because they act as, um we can add different metals in space in these interstitial sites. All right, so basically hydrogen, carbon and nitrogen, all right, they get trapped in this crystal lattice, in this, at that interstitial positions. Okay, which result in increasing their high melting point and boiling point, and obviously they are chemically inert, okay, and good conductor of electricity. All right.